Welcome to the deep dive.
Mm.
Ever wonder what's really happening behind the scenes when you use an app or browse a website?
Hmm.
Chances are it involves something called a database
Hmm.
and probably a language called SQL.
Right. SQL. Sounds technical, maybe?
It can sound a bit techy, yeah.
Yeah.
But our goal today is really just to pull back the curtain a bit,
Yeah.
make these fundamental concepts clearer for you.
Exactly. We're drawing from our source today, lecture1.pdf, just pulling out the key stuff.
Uh-huh.
The mission really is to give you a solid foundation. What are databases? How does SQL, that structured query language, how does it actually let us talk to them?
Okay, so sort of a starting point for understanding how all that digital info is well managed.
Precisely. Your first step into that world.
All right, let's dive in then. From the very beginning, what is a database?
Fundamentally.
Okay, so at its heart, a database is
Mm.
it's a system for storing data, but in a really organized way.
Like a digital filing cabinet. Is that a fair analogy? Yeah, that's a pretty good way to think about it. A meticulously organized digital filing cabinet. It holds all sorts of information, customer details, product info, anything really.
And the structure is important.
Oh, absolutely crucial. It's what lets us find and manage specific bits of information efficiently. Without that structure, it's just a data swamp.
Okay, got it. Organized data storage. So then, if it's all neat and tidy, why do we need this extra thing, SQL?
Ah, good question. So the database is the organized cabinet, right?
Right.
SQL is, well, it's the language you use to interact with it. It's the set of instructions you give.
Instructions for what? Finding things.
Finding things, yes. But also adding new information, changing existing stuff, even removing data. It lets you ask very specific questions.
Queries, you call them.
Exactly, queries. To get precisely the data you need, our source mentions needing to formulate some queries and then translate these to SQL queries. That's the core idea.
Okay, so SQL is how we ask the digital librarian for exactly what we want. Now, the lecture also goes beyond just basic SQL queries. It mentions other ways to interact, like views. What's the deal with views?
Right, views. Think of them as customized perspectives on the data.
Customized perspective.
Yeah, so the whole database might have tons of information, right, for everyone in a company, but a view for, say, the sales team might only show them customer names and maybe their purchase history, none of the other stuff.
Ah, I see. So it filters things out for specific users.
Exactly. The source talks about external schemas, different ways users see data. Views are how you implement that. You create a tailored view that includes only the specific part of the database that a user or a group of users needs to see.
Okay, that makes sense. Why bother doing that, though? Why create these separate views?
Well, there are a few really good reasons. First, as we said, tailoring the data. Custom views for different teams or users.
Like the sales example.
Right. Accounting sees finance data, marketing sees campaign data, all from the same underlying source, but nobody gets bogged down in irrelevant stuff.
Okay, efficiency. What else?
Security is a huge one. By using views, you can enforce data security by restricting access to a subset of the database.
Ah, so people only see what they need to see.
Yeah.
Nothing more.
Precisely. It helps protect sensitive information, like showing someone only specific pages from that filing cabinet, not the whole drawer.
Got it. Sensitive data protection. Anything else?
Yep. There's also data abstraction. Views can hide the complexities of the underlying database structures from the users.
Meaning?
Meaning the actual database tables and how they're linked might be really complicated behind the scenes. A view can present a much simpler picture, makes it easier for non-technical users to work with the data.
Okay, hides the messy bits. And the last point was independence.
Right, independence. This means that changes in the conceptual schema can be absorbed without affecting the external schema.
So if the database structure changes underneath?
As long as the data needed for the view is still technically available, the view itself and the person using it might not even notice the change. It adds a layer of insulation.
That sounds really useful. Prevents things from breaking every time the database gets updated.
It definitely can save a lot of headaches, yeah.
Now, the lecture did mention something about limitations. You can't always update data through a view.
That's true. It gets tricky. Generally, if a view is basically a direct window onto a single table without complex calculations or combining data from multiple places, then you can often update through it. But if the view is doing more complex stuff like summarizing data or joining tables, the database might not know how to translate your update back to the original source tables correctly.
So simple views may be updatable, complex views probably not.
That's the gist of it, yes. The source lists some specific criteria like needing to be based on one table, including key columns, no aggregate functions, things like that.
Okay, makes sense. Let's move on to indexes. Now, I think most people get the idea of book index helps you find stuff fast. Is it the same concept here?
Exactly the same idea. The lecture poses the question, right? How does the DBMS retrieve a row? The basic way is just looking through everything, page by page, sequential scan.
Which sounds slow if you have a lot of data.
Can be very slow.
Yeah.
So indexes are these hidden derived data structures used for speeding up certain queries. Just like a book index lets you jump to the right page without reading the whole book. A database index lets the system quickly find the location of the specific data it needs without scanning the entire table.
The notes give an example. Creating an index on an airport table's code column. How does that actually speed things up?
Okay, so when you index the code column, the database creates a separate sorted list of just those airport codes. And next to each code, it stores a pointer, like an address, telling it exactly where the full record for that airport is in the main table. So if you query for, say, code AMS, the database doesn't read the whole airport table. It zips over to the index, finds AMS super quick because it's sorted, grabs the pointer.
And jumps right to the Amsterdam record.
Exactly. The notes say something like 3 steps in index instead of scanning all rows. It's a massive performance boost for those kinds of lookups.
Wow, okay, that's a big difference. What about these composite indexes and the most left prefix thing mentioned? Sounds a bit more involved.
Just means you can create an index on more than one column, like maybe on last name and first name together.
Okay.
The most left prefix rule just means the index is most useful if your query uses the columns in the order they appear in the index, starting from the left. So an index on last name, first name works great if you search by last name or by last name AAD first name.
But maybe not so great if you only search by first name.
Exactly. The order matters for how efficiently the index can be used.
Got it. So indexes sound amazing for speed. Are there any catches? Any downsides?
There's always a trade-off, isn't there?
Usually.
Indexes speed up reading data, your queries, but they make writing data inserts, updates, deletes a bit slower.
Oh, why is that?
Because every time you change the data in the table, the database also has to go and update any indexes that include that data, keep them in sync.
I see. So more indexes mean more work when data changes.
Right. It's a balancing act. You index the columns you search on frequently, but maybe not every column. And, as the notes point out, managing indexes is typically a job for a database administrator, a DBA. It's usually transparent to the application developer just using the database.
Okay, so some behind-the-scenes tuning involved. Let's switch gears a bit. How do applications, the software we actually use, connect to these databases? The lecture talks about database connectivity.
Yeah, this is crucial. Your app needs a way to talk to the database where its data lives. The lecture covers a few main ways this happens. First up is JDBC.
JDBC, Java Database Connectivity, originally.
That was the original acronym, yeah. Though they say it doesn't officially stand for anything now. But basically, it's a standard Java API, a set of tools and protocols for connecting Java applications to databases.
Okay, so it's a Java thing. What does it let the application do?
It lets the Java code connect to the database, send SQL commands over, get the results back, manage transactions, things like that.
And it needs drivers, right? Like printer drivers.
Exactly like that. Each type of database, PostgreSQL, MySQL, Oracle, has its own specific JDBC driver. The driver acts as the translator between the standard JDBC calls the Java application makes and the specific way that particular database understands things.
So if I'm writing a Java app, what are the steps using JDBC? The notes outline a process.
Yep, there's a typical flow. First, you load the JDBC driver for your database, tell Java which translator to use.
Okay.
Then you define the connection URL. That's basically the address of the database server name, port, database name.
Like a web address, but for the database.
Sort of, yeah. Then you establish the connection using that URL, and usually a username and password.
Makes sense. Need credentials.
Once you're connected, you create a statement object. This object is what you use to actually send your SQL.
Okay.
Then you execute a query or update. There are more methods like execute query for select statements that return data and execute update for things like insert, update, or delete.
And if you get data back?
You need to process the results. They usually come back in something called a result set. And finally, very important, you close the connection when you're done to free up resources.
Right. Clean up after yourself.
Yeah.
The notes showed some Java code snippets for loading a driver and the URL.
Yeah, just illustrating those first couple of steps.
And there's a distinction between statement and prepared statement. What's that about?
Both let you run SQL, but prepared statement is generally preferred. It's often more efficient if you run the same type of query multiple times with different values because the database can pre-compile the query plan.
Ah, efficiency.
And crucially, it helps prevent a major security vulnerability called SQL injection. So generally better practice to use prepared statement.
Okay. And the results come back in a result set. How do you work with that?
Right. The result set is like a little table holding the data your query returned. You typically loop through it row by row using its next method. And for each row, you use get xxx methods like get string, get ding, to pull out the values from the specific columns you need.
Okay, so you iterate and grab the data. There was also result set metadata mentioned.
Yeah, that's like asking the result set about itself. It can tell you things like the names of the columns, their data types, how many columns there are. Useful for more dynamic processing sometimes.
Got it. So JDBC is a pretty direct way for Java apps to send SQL. What about stored procedures? That was another method mentioned.
Right. Stored procedures are different. There are chunks of SQL code, sometimes quite complex logic that you save inside the database itself.
So the code lives in the database, not in the application.
Exactly. Think of them like little programs stored in the database that you can just call by name from your application.
Why would you do that? Why not just keep all the SQL in the application code?
Several potential benefits. One is reduced network traffic. Instead of sending potentially many lines of SQL from the app to the database, you just send one command. Run this procedure.
Okay, less chatter over the network.
Yep. Also, the database can often pre-compile and optimize the stored procedure code, so it might execute faster.
Performance again.
Performance, yeah. And security. You can grant permissions to execute a specific procedure without granting direct access to the underlying tables. It adds a layer of control.
Ah, interesting. Control access through the procedure itself.
Right. And it also encapsulates logic. The application just calls the procedure. It doesn't need to know the messy details of the tables the procedure might be working with. Hides complexity.
The notes had an example, movies off factor. How would my Java app run that using JDBC? Is it different?
It's pretty similar. You typically use a special kind of statement object called a callable statement designed for stored procedures. You'd set any input parameters the procedure needs, like the actor's name, and then execute it. The results, if any, often come back in a result set, just like with a regular query.
Okay, so similar process, just a slightly different object to call the database's internal program.
Pretty much.
All right. Now, the last connectivity method listed was ORM, Object Relational Mapping. This sounds different, more abstract.
It definitely is more abstract, yes. ORM is a higher level approach. Instead of you writing SQL, you primarily work with objects in your programming language like Java objects or Ruby objects, whatever you're using. The ORM framework acts as a bridge, automatically translating your actions on those objects into database operations.
Whoa, so I wouldn't write select from customers where it equals 5.
Probably not directly, no. You might have a customer object in your code. You'd tell the ORM framework, hey, find me the customer with ID 5, and the ORM would figure out the SQL needed, run it, get the data, and create a customer object for you filled with that data.
That sounds easier.
It can definitely speed up development. The lecture contrasts JDBC, which it calls a call-level interface, you make direct calls, with ORM. The idea with ORM is you define your data classes like customer product as persistent classes.
Persistent meaning they stick around in the database.
Exactly. The ORM handles saving them to the database, loading them back, updating them, deleting them. It manages that mapping between your code's objects and the database's relational tables.
Examples mentioned were JPA Hibernate for Java and Active Record for Ruby on Rails.
Right. Those are very popular ORM frameworks. They handle a lot of the boilerplate database interaction code for you.
So what's the general workflow with an ORM?
You typically define your entity classes, the objects representing your data. You map their properties, like customer name, email, to database columns, often using annotations or configuration files. The ORM usually provides basic methods like save, find, delete. For more complex things, you work with your objects and relationships, and the ORM generates the SQL behind the scenes. The notes link this back to good programming practice, trying to make database work cleaner.
Okay, focus on the objects. Let the framework handle the database translation. What are the pros and cons here? Sounds like faster development is a big pro.
Definitely. Fast development is key. ORMs are often fairly scalable too, and they can make it easier to switch between different database systems because your code isn't tied directly to, say, PostgreSQL-specific SQL. It works with the ORM's API.
Okay. Easier database portability. Any downsides?
Well, that abstraction can sometimes be a disadvantage. Because the ORM generates the SQL, it's not always transparent what happens. The generated SQL might not be the most efficient, and debugging performance issues can sometimes be trickier. Performance can be less predictable than handcrafted SQL for really complex queries.
The magic can sometimes hide performance problems.
Yeah, that's a good way to put it. There's a trade-off between convenience and control transparency.
Okay, wow. We've actually covered quite a bit of ground in this deep dive.
We really have.
We started with the basics, what a database actually is, that structured storage.
Right, the digital filing cabinet.
And then why we need SQL, the language, to actually ask questions and manage the data in that cabinet.
The instructions for the librarian.
Then we looked at ways to refine how we interact. Views, for giving tailored and secure perspectives.
Hiding complexity.
Indexes, for speeding up those queries, like the book index analogy.
The performance boosters, but with that update trade-off.
And finally, the different ways applications actually connect. The direct approach with JDBC, using stored procedures living inside the database.
Yep, reducing network chat potential speed gains.
And the more abstract ORM approach, working with objects instead of raw SQL.
Letting the framework handle the database details, for better or worse sometimes.
So really this was about laying that foundation, wasn't it? Giving you a clearer picture of these core concepts.
Exactly. Databases underpin so much of our digital lives, and SQL is that fundamental language. Understanding these connection methods just shows the different strategies developers use to bridge the gap between applications and their data. Hopefully it's a solid starting point for anyone listening.
Absolutely. So here's something to think about as we wrap up. The next time you're using an app, maybe booking a flight, ordering food, whatever it is, just pause for a second. Consider how these ideas, structured data, queries, maybe views or indexes working behind the scenes, might be making it all possible. What part of that interaction, now that you know a bit more, seems most interesting or maybe even surprising to you? What might you want to dig into next?
Yeah. Good food for thought.
That's your takeaway from this deep dive. Thanks so much for joining us.